Hi, okay, so we are going to, let me go ahead and move this stuff around. All right, so state the possible rational roots for each function, then find all the rational zeros. So remember, that's when you need to tell me the number of imaginary roots, the number of positive roots, the number of negative roots, and the number of rational roots. And so here's a refresher on how you find them. The imaginary roots, you're looking at this exponent right here, the lead exponent, the highest degree exponent. And remember, imaginaries come in pairs, so they only come in two. So you're either going to have 0, 2, 4, 6, and so on. If the exponent is 3, the most imaginary roots it can have is 2. When you're looking for positive roots, you count the sign changes. So you're looking at here, here's a positive, that's a positive 4x to the third, plus 9x squared, plus 6x, plus 1. All the sign changes, all the signs are the same, so there aren't any sign changes. When you look for the negative roots, you negate all of the x's. And remember what I taught you, when you negate the x's, the even roots, what's a negative times a negative? It's a positive, so I didn't leave enough room to. So you're really only going to be changing the signs of any of the odd roots. So a negative times a negative times a negative is a negative times is positive, so there will be a negative sign there. A negative times a negative for x squared stays positive. This x in here would be negative x. Negative times a positive is a negative. And then the sign in front of the constant gets brought down. So now you count the sign changes. Well, from here to here, that's a sign change. From here to here, that's a sign change. From here to here, that's a sign change. So that's how you find the negative roots. And then the rational root theorem says this, that if you take the factors of the constant and divide that, factors of the constant, which is the number without variables attached, divide that by factors of the lead coefficient, that will tell you the possible roots of this polynomial, possible rational roots. So let's go ahead and do that. The numerator, or the constant, is just 1, so it's going to be a possible positive or negative 1. And the denominator, the factors of 4, positive 1, positive negative 1, positive negative 2, positive negative 4. So when we sum all this up, here we have it. For imaginary roots, there's either going to be 2 or 0. And remember, when we're finding roots, we count down by decreasing values of 2. So here's the exponent of 3. So the most that we're going to have is 2. And if we subtract 2, we get 2 or 0. For positive roots, there were not any sign changes. All of them were positive. So there will be 0 positive roots. And then when we negated all of the x's, it became negative 4x to the third plus 9x squared, subtract 6x plus 1. So it went from negative to positive, from negative to positive, and there were 3 sign changes, but then we subtract 2, we get 3 or 1. And then when we look at these roots, remember there's a divide sign there, so the possible rational roots are positive or negative 1, because 1 divided by 1 is 1. 1 divided by 2 is positive or negative 1/2. 1 divided by 4 is positive or negative 1/4. And you take this information and you look at the original polynomial the first thing you should ask yourself is, could I do the grouping method? Is that a simpler way? And if it doesn't look like it'll group, you're going to go ahead and use synthetic division. So remember, when you're using synthetic division, and I'm just going to bring this all the way down, you take the coefficients and the constant number, and you go ahead and write them down like I've done here. Then you try these roots, either the positive or negative 1, positive or negative 1/2, positive or negative. Although we can rule out, in this case, we can rule out any of the positives because, remember, there were no sign changes when we were looking at positive roots, so we only need to try negative 1, negative 1/2, negative 1/4. That's why it's really smart to check the imaginary positive and negative roots, because it's going to save us some time. So we're going to try negative 1. So negative 1 times 4. Remember, when you set it up, you write down the coefficients and the constant, you draw a line, and you always bring down that first number. And then you multiply. Negative 1 times 4 is negative 4, and then you add these together. 9 plus negative 4 is 5. Negative 1 times 5 is negative 5. And then add 6 plus negative 5 is 1. 1 times negative 1 is negative 1. 1 plus negative 1 is 0. Because this is a 0, one of our roots, here we have it down here, is negative 1. Now we can start the process again, and now we just have these three numbers to look at. And we carry down that 4. I'm going to try negative 1 again. Remember, you can have duplicate roots. Negative 1 times 4 is negative 4. 5 plus negative 4 is 1. Negative 1 times 1 is negative 1. 1 plus negative 1 is 0. So x equals negative 1 again. Now we're going to bring down that 4, and we only have two terms. Well, what would I multiply 4 by to get it equal to negative 1? Negative 1/4. Negative 1/4 times 4 is negative 1. 1 plus negative 1 is 0. Our third and final root. Remember, the fundamental theorem of algebra tells us that with a polynomial, there's always at least one root, but if we look at that exponent, it tells us the maximum roots that it can have. The maximum this polynomial can have is 3 roots, and remember, if we look back here, there were going to be 3 or 1 negative roots, and we have 3 negative roots. So in our solution set, we would have negative 1, and that's a multiple of 2. Or if you want to put negative 1, negative 1, negative 1/4. That's a fine way to do it also. All right, that's it. That's how you use these different theorems to figure out the roots. And remember, these roots are also called the zeros. It is where this graph, so at negative 1, and at, I should have done that bigger, and at negative 1/4, that graph is going to hit the x-axis. That's what the zeros mean, or the roots mean.